Hi, Fraser.
Hi,
You're not looking so well today.
I'm Fraser Cain. This is the closest I can find to a bald cap, guys. Hi, I'm not Fraser Cain. Welcome to the Weekly Space Hangout. I'm Nicole Galucci with the postdoc with CosmoQuest. Fraser is in Austin, Texas right now. I'm sure having a lovely time. So he cannot be hosting this week. So they made the very unwise decision to put me in charge. And I have with me Brian Koberlein.
Hi.
Hi,
Hello, Nicole.
Brian.
Hi.
And Morgan Renberg.
Hi, Nicole.
So we are going to give you some of our top hits from the space astronomy news from this week. We have, what do we have in the spreadsheet? We have Saturn. We have maybe a moon rover that has survived. We have a milestone for the Mercury Messenger program, a second-generation star, and I'll hopefully have some Valentine for you, as well as a couple of other things that we'll talk about today. If you want to participate, we'd love it when you guys participate. There are a few ways to do that. You can use the Q&A app through Google Hangouts or YouTube. We can set up on the side. We have a Happy Valentine's Day from Rich. We have Why Gesticulating Towards Monitor from Tom. And a hi from Nancy, so hi everybody. That amuses me. And hi from Andrew Planets. There are two event pages. There's one event page associated with the Hangout, another one associated with the CosmoQuest page. You guys can comment there, and we will check that out as well. I'll try and post the links to the articles on the CosmoQuest event page. You can use YouTube comments. I will try and keep track of that. We're going to keep track of all comments for you. We're going to do the best we can. So please ask us questions and say hello and all that fun stuff. I think we should start in our very own solar system. Morgan, maybe you can tell us a little bit about these new Cassini images.
Yeah, so a couple of these Cassini images have just been floating around the interwebs the last couple of weeks, and I thought I'd try to put a little context to them because it's not always obvious with these pictures what exactly we're seeing. So I'm going to attempt the always dangerous screen share.
Sure.
All right, can you see that?
Yeah, there we go.
All right.
Yeah.
So this is a gorgeous image
Wow.
that was taken by the wide-angle camera on the Cassini spacecraft. And obviously here we're looking at Saturn, and we're looking down from basically the north of Saturn. And what we see here is what's called the North Polar Hexagon. If I can just center that for us here, you can see this very hexagonal shape. It's almost a perfect hexagon, right sitting on the North Pole of Saturn. And this is one of the most interesting atmospheric features in anywhere in the solar system, really, because while we see these hexagonal features other places in the solar system, they only usually last for a really short time, hours, minutes. This one's has lasted since at least 1980. So this is a storm basically in the North Pole, at the North Pole of Saturn, that's been raging in this hexagonal form for at least the last 30 years, and it's been observed by both Voyager and Cassini. And it's still kind of a puzzle how you get something like this, but people have been working on the problem with experiments in the lab, and they can get shapes similar to this by rotating fluids at different rates. So the fluids on the inside, the center of the hexagon, are rotating more slowly than the fluids on the outside. And if you do that just right, you get this hexagon, where sometimes you get an octagon or a pentagon, but on Saturn we get a hexagon. And the fluid that we're talking about here is actually the atmosphere of Saturn. So what we see here basically is we can see the shape and the direction of the winds at the North Pole of Saturn. Yeah. And we've seen this several times now with Cassini over the last few years, but this is definitely one of the prettier pictures we've had to see.
That's gorgeous. Mm-hmm. Yeah, the hexagon is a special place in my heart because it's the first thing I blogged about on the Discovery Channel blog. So it was one of those lab experiments. They had this glowing green gas that they were using to simulate the hexagon.
Yeah, it's remarkably stable to have been here, for the last 30+ years. And I think, we often think of the outer planets as being a lot more static than the inner planets or the rocky bodies. We think of, the winds and dunes on Mars or volcanoes on Io or the geysers on Enceladus, we don't really think, aside from maybe the Great Red Spot, we don't really think of the outer planets as being active places. But they're incredibly active, and in fact, the forces that shape planets like Jupiter and Saturn are far more powerful than those that shape Mars, Venus, even the Earth. But because the planets are so big, things don't seem to be moving as fast, even though they're moving far more violently than we see elsewhere in the solar system.
Sure, sure. Do you have that F-ring gift as well?
I do. Yep. So that's our second one here.
I love this.
Shamelessly stolen from Jason Major. So
Thank
thankfully
you,
he's not here today. So I'm going to flip quick here over to our handy-dandy diagram of Saturn's rings.
Hey.
Thank you, Wikipedia. And so here are the main rings, A and B. This is what you'd see if you pulled out your telescope at home and pointed it at Saturn. Where we're looking today is out here at the edge, the F ring. This is the outermost of the main rings of Saturn. It's the most tenuous of the main rings of Saturn. And you'll see that it just forms this narrow little strip right outside of the A ring. And right outside the F ring is the orbit of a moon called Prometheus. And that's what we're seeing here in this image, is as it goes through, we see Prometheus skirting right along the F ring. And while it's not really touching the F ring, it can interact with it using gravity. And so as it goes by, we see behind it these waves are launched, and the waves sort of move upwards and even a little bit downwards in the image. And these are kind of like the gravitational equivalent of boat wakes, that as rather than pushing the material out like a boat does, as Prometheus goes by, it's bunching the material up because it's attracting it gravitationally, and then after it goes away, that gravity's gone, and the material relaxes outwards and forms these waves. And this is really important, actually, in the F ring, because the F ring is right sort of on the edge between being able to make solid bodies like moons, which would be further out, and having all of those things ripped apart, which is why the inner rings are so flat and so uniform. And the F ring lies right at the edge of that. It's actually trapped in that area. And Prometheus, going by like it does, stirs that area up and causes particles in this area to clump up. And they clump up, and then they're broken apart by Saturn's gravity, and then they clump up again, and then they're broken apart. And it's just kind of ebbing and flowing of the ring that forms these very complicated, twisted structures at the center of the F ring.
So Prometheus would be called Shepherd Moon then, because it's shepherding the ring into place?
Right. So there's some debate about what moons, if any, actually shepherd the F ring. There's also a couple of other moons nearby called Janus and Epimetheus, and they also play a role in confining the F ring to this area. But there certainly are places in the solar system where we have these moons, shepherd moons, that keep the ring, a ring, very tightly confined. We see it at Jupiter, we see it at Uranus, and they make these really narrow, sort of strand-like structures that are just really beautiful.
We have a question about the previous image from Tom Nathan asking, it's hard to tell from the photo, but does the center have a spiral pattern as well? Has any of that been picked out in some of the studies?
I believe that there is a spiral pattern. There's at least one color video that was taken a couple of years ago. And I believe that this area is kind of spiraling around, and if I zoom in here, you might
see swirl.
Yeah, you might sort of see, you see kind of a swirling path here and here. But for some reason, and it's not really well understood, that swirling stops at the boundary of this hexagon and forms these sharp lines. And then again, we kind of have swirling out here, and then you kind of imagine there being a second boundary out here. And then once we get farther south than that, we just rejoin the normal flow of the winds on Saturn.
Very cool. Very cool. We have a couple of commenters in Hugo and Guido in UK and Britain, or sorry, in UK and Germany, talking about their storms at the moment and realizing that Saturn's storm totally beats all of our storms. So.
Oh, yeah, one other thing that I could mention is that on each side of the hexagon, you could comfortably fit the Earth.
Oh, wow.
So yeah,
Yeah.
so
That's
to
huge.
give you some scale, we're talking about many Earths across, and you could stack Earths up along the outside, and that's the size of the storm. So smaller than the Great Red Spot, but bigger than anything else that we see out there in the solar system.
We have Ryan Schmitz asking, what is the object to the right below the F ring in that image? Is there something? It
Let me bring it back up here.
looks like there's a couple of spots that might be.
Object to the right below the F ring?
Yeah, I'm seeing a couple of spots come up here and there. They look like they're image artifacts, like cosmic ray
it's
hits.
likely that they're cosmic ray hits,
Yeah.
or something like that. So the imager is detecting light as it reflected off Saturn, but there's also very highly energetic particles coming from outer space, and if they happen to hit your detector, they form just a really bright flash for basically just one image. And that's what we see, and they're all over images in astronomy, and they're a pain to deal with.
Well, speaking of particles, we have a segue. Brian, you have a story on a measure of the mass of neutrinos. Let's hear a little bit about that.
Yeah, this is kind of an interesting thing. It is, if you look at the neutrinos, there's the history where the original idea of neutrinos is that they didn't have any mass. So the initial proposal was that, and this led to what was known as the solar neutrino mystery.
Mm-hmm.
And basically, the solar neutrino mystery is if you calculate how many neutrinos the sun is producing based upon its nuclear reaction rate, we see a third of that. We see only a third of what we would expect to see. And over time, we resolved this by recognizing that what happens is there's actually 3 different types of neutrinos, and they can switch between different types. So when a neutrino travels through matter, it can switch between different types. And so what happens is they kind of randomize. Their electron neutrinos are produced in the center of the sun. They randomize as they come out of the sun, and then we see the ones that happen to be electron ones, but the muon and tauon neutrinos we don't see. And we've since been able to detect muon neutrinos, and we can do these types of experiments. So we know neutrinos have mass, but the mass of the neutrinos is extraordinarily tiny. And so the question is just how much mass it is. Trying to do an experiment in the lab is difficult to try and pin down what the mass is. So one of the things that you can look at is cosmological aspects. Well, the interesting thing about this new paper is they've done some cosmological limits based upon, say, how much galaxies cluster. So you can look at what's called the baryon acoustic oscillation, or BAO, and it tells you basically how galaxies cluster at different scales. Based on that, you can kind of put an upper limit on what the mass of the neutrinos were, because if they had more mass than that, then the galaxies would cluster differently. Well, this leads into another aspect of kind of cosmology astronomy, which is we have different ways of measuring the structure of the universe. So things like the Hubble expansion constant, things like the scale and all of this. And the different measures that we have, they agree, but they're always just a little bit off. So if you say, how much dark energy do we have based upon the baryon oscillation? That's one value. And how much do we have based upon the cosmic microwave background? That's a slightly other value. And how much do we have based upon gravitational lensing? That's a slightly different value. And they don't quite line up. Their uncertainties overlap, so they agree in that sense, but they don't quite line up. This new paper looked at, given that the fact that the neutrinos have mass, if you include the mass of neutrinos into these various observations, how does this affect them? And what's interesting is that when you do the calculations, what you find is adding neutrinos into the mix actually makes them agree better. So the ones that are too low skew up a little bit, the ones that are too high skew down a little bit, everything matches up a little bit better. So they took what the best fit of all of these were, like what possible mass the neutrinos have, and what they got was that if you take all 3 types of neutrinos, if you take all 3 flavors of neutrinos, the total mass of one of each would be no more than, would be 0.32 plus or minus 0.081 electron volts. So they've narrowed down, they've got a pretty good measurement of what the total mass of the neutrinos in terms of the different flavors would be. And yeah, go ahead.
Yeah, is there a theoretical basis for estimating the mass, or is it all being done experimentally?
Well, you can have different ideas in terms of what the mass is, but the mass is tiny. Basically, you tweak it to include mass. So I mean, the original idea of the standard model, the kind of simple version, was, oh, they have no mass. So neutrinos have no mass. But because they change flavor, you add mass. So you can modify the standard model, and this modified with neutrino mass standard model is now the standard model of particle physics. But if you look at these are far lighter. These are far less energy than the mass of an electron, for example.
Right, that's 500,000 eV.
Yes, and this is yeah, it's 500,000 electron volts. This is 0.3 electron volts. So it's that much tinier, and that's for all three flavors. Mm-hmm. So there's another experiment that they've done in the lab that I think is the lightest one can be no more than 0.06 electron volts. I think that's right. So we're talking extraordinarily tiny masses. But part of what I find really interesting about this is how, in this paper they laid out how it actually makes different parameters work better. So there's this thing that we talk about called the tension between different views. So you have this experiment and this experiment. They fit, but we'd like them to fit better. They're just a little bit off. And adding the neutrinos into the mix actually makes them fit better. It actually makes them agree. So you can actually use that agreement now to put a constraint on what the neutrino mass is, which is really cool.
It's clever.
So the neutrinos aren't constraining cosmology. The cosmology is constraining the neutrino mass.
Exactly.
That's pretty cool.
Based
so
upon
observing the universe,
yes,
you could constrain the mass of a neutrino.
I mean, basically what you're doing is you're saying, here's the cosmic microwave background, and here is the distribution of galaxies for gigaparsecs out. Mm-hmm. And then here is gravitational lensing that occurs all the way out. So you're looking on, gigaparsec scales, and
that's billions and billions of light years.
That is a fraction of the mass of the electron.
Yes.
Which is just it blows your mind when you think about it.
The convergence with particle physics and cosmology that's happening now. We have to understand what's happening on a tiny scale to understand what's happening on the grand scale of the universe.
Exactly, because it all adds up on that grand scale.
Mm-hmm. So we have a question from Hugo. So if the neutrino has mass, even a tiny bit of mass, can it then not travel at the speed of light?
It does not travel at the speed of light.
Is it really, really close?
It can get close to the speed of light. There was the 1987 supernova, where we saw the spike of neutrinos before we saw the light come to it. So it was, we saw the light before we saw the spike of neutrinos. So we know.
Right.
We know that the neutrinos aren't traveling at exactly the speed of light. They can't.
But the light also takes some time to get through junk around the forming supernova. It
does, but not in a significant way.
Not significant. Okay.
Yeah.
And Mark Gillick asks, do different neutrinos, I assume this is different flavors, travel at different speeds?
Good question. I don't know.
Stump the astrophysicist.
Stump the astrophysicist.
You'd imagine they would if they had different masses.
That's what I would imagine. And the usual idea is that you're going to have them, that they're not going to be degenerate in terms of mass. They're not going to have the same mass.
Okay.
So you would think that just as the electron, muon, and tauon have different masses, you would expect their corresponding neutrinos to have different masses. Right. But we don't know. There's it's not entirely clear yet.
And I want to clarify one thing when you flavor of neutrino. We're not talking about you can taste neutrinos. Particle physicists have interesting ways of distinguishing between different types of particles. Just want to clear that up.
Absolutely, yeah. When we say flavors, we just mean different types.
Yeah, I don't know. I think they got a little bit cheeky when they started running out of ways to describe physical properties that don't make sense to us in the macroscopic world.
Right.
So you have flavors of, and you have, top and bottom quarks and all kinds of interesting names for properties. And I remember asking my physics professor in college during a particle physics class, what does it mean? It doesn't mean anything. He goes, what does mass mean? And I went,
Yeah. My understanding was that when they were first developing particle physics, they had up all these internal names that they were using to talk amongst themselves, and they never planned for it to actually be a thing. But then they published their first paper, and exactly that. What do we call them? One name is just as good as another. Yeah. And so we end up with top and bottom and strange and charm and all the silly names we have.
The one I like with quarks, and I'm not sure if it's true, but that early on they were using cyan, magenta, and yellow, the different things for light colors. but when you try and use them on a overhead micro sheet and you try and do it with markers, you don't have yellow. It doesn't show up well. So you change it to red, green, and blue.
Oh my gosh, that's funny. Oh, amazing. Scientists sometimes practical, believe it or not.
Yeah.
Shiny.
Yeah. It makes sense to us.
Yeah, it does. Sorry, the rest of the world, you're stuck with it. So I brought a solar system related story because, unlike Fraser, I'm going to do that. It doesn't bring stories. I can bring stories. I'm having trouble showing the image to screen share, though, of course. So there was a new, an anniversary. Actually, this happened at the end of last week, but I don't think we got to talk about it. The Messenger spacecraft, which is currently orbiting Mercury, and has been since 2011? 2011, yeah. Reached a new milestone. It's taken 200,000 images of Mercury's surface. Guess how many they originally planned on for the mission? Anybody?
It was something like 1,000 or 2,000, wasn't it?
It was exactly. It was 1,000, and they thought, well, maybe we could compress some of it and get 2,000 images. Well, the mission, after 2 mentions, the mission has passed that by 100 times. So we've got a lot more of the surgery than we ever expected to see. So I just wanted to show off the new mosaic they sent out to celebrate that. So this mosaic of several images across a large crater there's a large crater on Mercury's surface. And if any of you are familiar from playing with moon mappers on CosmoQuest, you immediately want to start circles and marking these craters. And you see some interesting light albedo features here. It looks like either I am not planetary science. Morgan, maybe you can tell me, are these hollows?
I'm sorry, say again?
Are those hollows?
Oh, I don't want to speculate.
Okay.
Either.
It looks like some kind of material has either slipped or done something funny.
Yeah, so often what happens at the edge of an impact crater is over time it kind of collapses in on itself.
Okay.
And that exposes what's fresher material underneath the surface. Gotcha. And so what you could be seeing there is basically like evidence of a landslide.
Okay.
But I wouldn't want to say too definitively.
Sure.
Without looking a little bit more.
Yeah, hollows are this feat. Look like images of hollows to me, but hollows are usually seen on the floor of crater, and those are holes in the surface that are only seen on Mercury, which Messenger helped discover. I think it's material that's fallen in, or it's an active, ongoing process. Know for sure what the explanation is, but that was my my question. So if anyone knows what this is, that's cool. And like I said, if you want to explore the surface of Mercury yourself, we have the Mercury Mappers project running on CosmoQuest, where we have lots and lots and lots of images of Messenger, which is pretty cool, from Messenger of Mercury, which is pretty cool. So congratulations, team, for surpassing their image count by a factor of 100. That's pretty impressive.
I think it's important with Messenger to always remember that when we got to Messenger in 2011, we had just as good an idea of what Mercury looked like as we do Pluto right now.
There you go.
We didn't know anything. I mean, we'd flown by it a couple of times in the 70s, but we'd only seen about a third of the surface. And so it wasn't until just a couple of years ago that we were able to map one of the closest planets to us in detail that better than what you might see through like a home telescope. And that's a pretty remarkable achievement.
I think it had a lot. Was there a reason other than just it wasn't high on the priority list?
It's difficult to get to Mercury. Yeah. You can't use the atmosphere to slow down to get into Mercury orbit because there isn't an atmosphere. B, you're really close to the sun, so as you go around Mercury, you change hundreds of degrees from the day side to the night side. So the whole Messenger spacecraft is designed to expand and contract as it goes around, and it has to have special radial or ways to radiate heat away. And so Messenger was the first time we actually tried to get into a permanent orbit. Previously, we just kind of skipped on by and headed into the sun. So it's just not easy to get to.
Yeah.
It's the same challenge that we'll have trying to orbit Europa or Enceladus or something like that.
Mm-hmm.
Right, yeah, that's also a good environment. Not a terribly good environment for spacecraft, but the better the technology, the more we can explore. Speaking of technology exploring, Morgan, you have an update on the Chinese rover Yutu. Is it alive?
Yeah, and speaking of temperature swings of hundreds of degrees,
there you go.
When we last left Yutu, previously on, Yutu was shutting itself down to try to weather the lunar night. And because the moon keeps the same face towards the Earth at all times, the night on the moon lasts 2 weeks, and the day on the moon lasts 2 weeks. And the difference between night and day can be over 300 degrees, because when you're facing the sun, you get all the same heat that we get here on the Earth. When you're not facing the sun, you get no heat from the sun, and there's no atmosphere on the moon to redistribute heat. And so staying warm on at the lunar night is very, very difficult to do. And so what Yutu was designed to do was kind of fold itself up into a cocoon and insulate its instruments to try to help last that night. And it didn't work. The cocoon mechanism failed to properly wrap itself up after the end of the second lunar day. So after it had been there for about a month, it was wrapping itself up for its second lunar night, and it didn't get there. And it left this really sad, very sort of heart-throbbing message to the people of Earth about how its exploration was coming to an end, and it was welcoming death, and all of these very sentimental things. But
Twitter?
Well, it was the strangest press release I've ever written or ever read, because they wrote it in first person. So it was the rover speaking to the people of the world. Yeah, it was the rover speaking to the people of the world. My masters have found a control abnormality. I'm told I will not last the night, but I am happy because I've gone where others have not. It was an incredible read.
Kudos to the Space Agency for that. That's amazing.
But it turns out that it may indeed have survived the night. So we switched back to lunar day, where Yutu is, a couple of days ago. And at first, they weren't getting any signals from the spacecraft. But they kept trying, because why not? And eventually, it seems like they've started to get some signals. And even some amateur sort of ham radio operators have reported hearing what I assume are probably encrypted signals coming from the spacecraft. It's too early to know what works, what doesn't. Is it still going to be able to be functional as an actual, scientific instrument? But, it's remarkable that it could survive 2 weeks at temperatures hundreds of degrees below what it was expected to survive at. And it's certainly exciting for the Chinese Space Agency to maybe have a shot at bringing it back and continuing the mission.
That's pretty exciting. Yeah, I first saw a tweet from Emily Lockton with a picture of the signal from radio enthusiasts, uhfsatcom.com. That's pretty cool. So, yay, you too.
Yeah.
Oh, and a news report, Bunny seems to be getting better. That there is evidence that he is awake. We will see. According to a translation of a Chinese news report.
Right. Jade Rabbit, or Yutu means Jade Rabbit in English.
Right. I like Bunny.
Bunny.
I like Bunny. So, all right, so we'll be watching that, and I included a link over to Emily's blog post about that on the pages, because she's on top of all the planet stuff. We love Emily. So, all right. Let's see. What else do we have? I want to hear about population 2.9999 stars.
Okay. This is a new star that's been discovered that basically it has no iron in its spectra. So I'm gonna try screen share.
Okay.
We'll see.
That doesn't work. I can try that.
Come on.
In the link. Oh, and Guido also pointed out, and I have the screenshot with me. Patrick Stewart was on The Daily Show as Yutu.
A must-see. Hilarious.
I put that as my picture for the virtual star party, so I don't have it on this computer. Brian?
Okay, so is this
I'm
working?
seeing myself.
There.
Yeah, there you go.
Is it working?
So
Yeah.
you can see
There we
the line?
go. Oh, wow.
Okay.
Please explain
So-
this graph to people.
Please explain this graph, absolutely. These are two line spectras of two different stars. So the top one, this is a typical star that is less metallic than us. And when we say metals in astronomy, what we mean is anything other than hydrogen and helium.
Because we're so discriminating.
Yeah, so the periodic table for an astronomer is hydrogen, helium, and
Everything else.
everything else.
I get yelled at by star formation for saying that because they love molecules, but whatever.
Yes.
Classical astronomy.
So this is a kind of a typical star. It's a little bit less metals than the sun, actually about 80% less than the sun. But you can see there's a whole bunch of lines here, and all of these lines are based upon what is in the atmosphere of this particular star, and it's just tons of stuff here. If you look at the one below it, this is the one that is the line spectra for the star that was just discovered. And
That's amazing.
right off the bat, you can see there's much less stuff. Okay, but basically, if you look at what's causing these line spectra, this is hydrogen here, basically. This one line is carbon, and then you've got calcium and magnesium. I'm trying to think. I think this is calcium and magnesium, maybe there. I'm not sure. And then some atmospheric blocking because this is taken from within the surface of the Earth. But this is incredibly clean. I mean, basically, if you analyze what elements are in the atmosphere, the only thing other than hydrogen and helium is carbon, calcium, and magnesium. And in particular, in this region, there's no iron. This has absolutely no iron in it, which is astonishingly strange because most stars will have some level of iron in it. What this means is one of the things that we try and look for is a star that came as early after the Big Bang as possible. So what might be first generation stars, what we would call population 3 stars. These first generation stars would basically just be hydrogen and helium, and nothing else. They would form, they become supernovas, they explode, and because of the nuclear fusion in their cores, they produce everything other than hydrogen and helium. So all of the carbon, nitrogen, and oxygen that you find in your body came from the internal cores of stars. And so the first generation stars explode, they throw off some of the carbon, nitrogen, oxygen, and iron, and then from the remnants of those, new stars would form. From the remnants of those, more stars would form. And so over time, because each of the stars are producing heavier elements in their cores, typically, the later the generation of the star, the more metals, the more stuff other than hydrogen and helium you would find. So in this case, we don't see any iron. We don't see much of anything other than hydrogen and helium. Because it's got a strong carbon line, this is not a first generation star. But because it has no iron and it has very little of anything else, this is a second generation star. So this specific star formed from the remnants of the very first stars of the universe.
Now,
Which is just...
Do we expect to be able to see the first generation of stars?
There's been a search for this, but we haven't found it.
So how old do we think
keep
this
looking
star
for
is?
these. I'm sorry?
So how old do we think this star is?
It's hard, because of the low metal level, it's hard to get an exact date. Because it's a second generation star, the estimates would put it probably on the order of being 3.6 billion years old. But that's just based upon the fact that, you know, if you look at when the first generation stars had exploded and were done, you know, no more than 800 million years after the Big Bang, you would start seeing them explode. So this would have formed after that, but not too far after that. So you put as a rough number of 3.6 billion, something like that.
Yeah, so the astronomers in their...
Oh, sorry, 13.6 billion.
Back to, yeah, okay, 2.6. I was going to say it's not too old. The astronomers in their amazing way of naming things. Population 3, Roman numeral 3, is the first generation of stars. Population 2 is you can't split 3 generation, but they're kind of groups. Population 2 are the older stars. They tend to live in the halos of galaxies. And population 1 are the most recent. So it's a little bad when you think of it that way, but that's because they were discovered as individual populations in the galaxy. Population 1 stars being the most recent ones that are in the disk of our galaxy. So population 3 stars are always this enigma because they were only hydrogen and helium, so they were pretty massive and couldn't have lived that long. So there won't be any in the neighborhood. There won't be any in the neighborhood. We'd have to actually be able to see them as they existed that far away.
Right.
Or that long ago.
What's interesting about this is not only that there's that there's a low level of iron, but there's actually no measurable iron in this star.
That's amazing.
So which is just incredible. So a lot of times when we talk about the metallicity of stars, we talk about the ratio of iron to hydrogen. And they do it on a logarithmic scale. So for the sun, it would be 0. For population 2, it would be about -1, which would mean it's about 10% of the iron that our sun has. This is no more than -7.1.
And that's a logarithmic. That's like 10
that's a logarithmic
power.
scale. So it's like
100 million.
Yeah,
we have,
parts million.
1/10 millionth of the iron. One of the authors of the paper said basically if you took the core of the Earth, which is about the size of the moon, and you took 1% of it and tossed it into this star, it would give it more iron than it has.
Wow. Okay. Wow. Couple of questions and comments. Hugo Burnham calls it an anemic star. This is absolutely true. This star could not donate blood, like I am been rejected. Rich Hayward asks how old the star is, and I think he may have asked that before you said it. So they think it's about 13 billion years old, almost as old as the universe. We
can't age it because of its low metallicity, but we can just kind of say based on where it would form, that would be about it.
Yeah. How is this old star relatively close to us? And
it is actually.
Why haven't we noticed it before? Asks Ben Gaisley.
It's not a matter of noticing it before. It's a matter of getting a good measure of its spectra, because I want to say it's about 6,000 light years away, but I'm not quite sure.
That's really close.
Yeah, it's fairly close. But the thing is, you don't have to go very far for a star like the sun to be extraordinarily faint.
Right.
You know, I mean, you get faint really fast as soon as you get far enough away, and so it is a challenge to be able to measure. Not only to see where the star is, but you have to measure the line spectra. So the starlight has to come in, and you have to put it through a diffraction grating and spread this all out and scan all the different wavelengths to get a pattern. And you have to do it with a certain resolution in order to see what these line spectra are. So that's the challenge. Finding there's a star is not a problem, but actually identifying the elements in that star is a challenge.
And the fact that there are so many stars, once you get to the level of professional grade telescopes,
right.
Taking spectra of all of them does take a long time.
Yeah, I mean, the real challenge is being able to identify stars and then do better resolutions of it. So you basically have to find regions in which you would think there would be low metallicity stars.
Right.
And then you do kind of a basic scan. Right. Yeah. You do a basic scan and go, okay, out of those we have some candidates. Let's look at some new candidates and look at the higher resolution of these. And so it's an incredible deal. I mean, the team that's doing this keeps looking for more and more lower metals, and with this one, they need a better spectrograph now.
Okay.
Because they cannot detect iron now. I'm sorry?
What telescope? Is this Hubble?
I'm not sure. I don't think it's Hubble. I'm actually not sure.
Let's go to the archive. It's not in the abstract, then what the heck?
Yeah.
How do you not have it in the abstract?
Why do you not have there?
Lazy astronomer. Why isn't all the information in the abstract? But prior to the archive, to the art version of the article, which is free to access for everyone, which I've in his blog, and I've linked to the blog, so you guys can all look that up.
It is there. I just don't remember.
See, I want to look at it now, but I should. You guys
I'm
look
not
it
an
up while we move
instrument guy.
on.
The engineers do this wonderful stuff for us, and we look at the data.
So Tom Nathy asks, to confirm our sun is at least a generation star. It's hard to...
I think it's hard to say. I think that's usually the common interpretation, is that ours is a third-generation star, which would mean that it formed from stars that formed from stars like the second-generation star, which then came from the first
so each successive generation becomes more metal-rich as more massive stars create these heavy elements in them, as more supernova create the rest of the periodic table.
Right. I mean, that's not perfectly true because it depends on the environment that you're in, but generally,
very generally,
next generation stars tend to have more metals than earlier generations.
Michael Jobin's asking, could the spectrum be filtered by something else in front of it that we don't know?
No, not in this case, because we have a clear line of sight. One of the things that you can see in the spectra is on that one end. You see a little bit of chaff on the right side, and that's actually from our atmosphere.
Right, so you can tell.
So the only blocking we're getting is really from the atmosphere, and it's not that far. There isn't that much gas and dust.
Right.
And they tend to absorb, not emit lines, so you would see the lines there.
Yeah, you'd see them or you'd see something funny in the velocity of the gas that was in the way.
Right.
Right.
That's the other thing, is that if we see an absorption line, we can see if it has a different Doppler motion relative to the star.
Right. Very interesting. I got to do a spectroscopy project when I was in grad school. Yeah, I did use an optical telescope once or twice.
Yeah.
And we had to compare the spectra of stars and classify them and do all that. It's pretty dicey. It's pretty cool though.
It's very cool. The fact that you can do that, you can see basically star rainbows, and you can do science with it.
Star rainbows, science. I love it. Okay, I want to ask you guys, what were you doing almost exactly a year ago today?
Oh, you with the meteor? I think I was teaching.
Major event?
I was sitting in class.
You were sitting in class. Where? Okay.
Or when I found out, I don't know where I was when it happened.
Where were you when you found out about the Chelyabinsk meteor over Russia?
It was after class. I was asked by one of our news media people. It's like, do you have a comment on this new meteor? What new meteor?
I'm working here, dude.
Like, no, let me go look at the news for an hour. I'll find out what I know.
What about you, Morgan?
Yeah, I think I was in class too. I think someone brought in one of those early Russian dashcam videos of it that was uploaded to YouTube, and from then on it was off to the races trying to see what was out there. I did not get woken up by you.
No, I think Pamela Gay is the only one I actually woke up by phone, and then either I texted Fraser or she texted Fraser after that. I don't know what I was doing, but I was on the computer at home, and Phil Plate and I and a bunch of us all started getting these tweets about, can you confirm this meteor over Russia? We're like, no, we're not in Russia. I don't. And like most stories of that type, you're really cautious and you're really skeptical at first. I mean, there are lots of things people see in the sky, and there are lots of hoaxes out there. But then the ones with sound started coming out. The ones, and we actually on the Weekly Space Hangout right after that we did a Space Rock special edition, because not only was Chelyabinsk going on, but there was asteroid 2012 DA14 did a very close pass to Earth, and they were completely unrelated events. So we did all the space rocks. That was what I was hearing. Yeah.
People said, did that meteor come in? Did it actually hit the Earth? It's like, no, it can't. It's not going to at all. It's like, no, but it hit in Russia. What? What are you talking about?
No, they were coming from completely different directions. Yeah, so that was cool. It's a nice Weekly Space Hangout memorable event because we all kind of got back online. I think I don't know what time it was. It was evening. It was nighttime, and Pamela had gone to bed early for once, and I felt kind of bad waking her up because she doesn't get much sleep as it is. But I got her out of bed to cover this one. So anyway, I have a piece of the Chelyabinsk meteorite
very cool.
here. There's a little piece of it, a gift from my buddy Richard Drum, who produces a 365 Days of Astronomy podcast right now. So this little chunk here, I don't know if this will actually come in focus a little bit. And I actually keep it in my purse for emergency science demonstrations. I tell people, do you want to hold a piece of a space rock? And they're like, yeah! This is actually what I do.
I'm going to have to remember that phrase. Emergency science demonstration. Stand back! This person needs science!
Exactly. Exactly! And that's
Back
you know
off,
what?
man. I'm a scientist.
It's fun. I'm a scientist. So yeah, so this is a contradict meteorite. You can see the little, sometimes if you have a hand lens with you, you can look at the little grains inside, and it's having trouble focusing on it. And then you can also see it's kind of scratched in places around the fusion crust when it came through and exploded and made a sonic boom that scared the pants off of about 1 million people. So anyway, so that we're celebrating the actual impact was on February 15th local time in Chelyabinsk, but it was February 14th here in the U.S. when we started hearing about it, and so let's make it a 2-day celebration. Why not?
That's right.
No, why
Plus
not?
dashcam astronomy. So
Dashcam astronomy. We learned a lot about dashcams. I think I linked in my CosmoQuest blog on it. I linked to an article that Ian O'Neill wrote for Discovery last year, just about the dashcam phenomenon.
Yep.
It was that's usually one thing of the hoaxes is how are there so many video? How could so many people have dashcams? That's got to be a hoax. No, that many people actually have cameras in their cars running in Russia. It's quite impressive. So celebrate Chelyabinsk today, guys. And it's also some other holiday today. I don't know. I don't really pay attention. Something with candy? Something with hearts?
Yeah.
So there are a couple of, so both Phil Plait on Bad Astronomy and Elizabeth Howell on Universe Today have put together some pictures of hearts in space. So here is a gorgeous, gorgeous nebula. It's an infrared view from the Spitzer Space Telescope. You can go down to some astrophotography where people have inserted their own hearts, and there are lots of craters and geological features. This one in particular is on the moon that sometimes have a heart shape to them. So I'll include those links in the comments. You guys can go check out those collections of heart-shaped astronomy things for the nerd in your life, romantic nerds in your life. I believe there was also a comment. I don't know if I saw this one. There was a picture from Mars. Oh gosh, Mars Science Lab Curiosity navigation camera photo had a Valentine shape in the sand this morning by its wheels. So, yay for Curiosity for doing that. Let's see if there's any other comments I can get to or questions. Yeah. Oh, sorry. One more thing. Susie. So Susie Murph, who's helping us produce these shows, said that the Olympic gold medalists also get in Sochi right now get another medal that contains a chunk of the meteorite in it.
Yes.
That I had not heard.
That's so
before.
cool.
Yep. I think
I hadn't heard that either.
That's really cool. That's being reported on space.com. That they are actually getting a medal with a piece of the meteorite in it. That's pretty awesome. I'm in favor of this. So I think that's all our space news for the week, unless you guys have anything to add.
No.
Nope.
I don't
Okay,
think
so
so.
let's run through. Let's do the shameless plug part of the show. So Brian, where can we find you and all of your awesome work?
You can find me at my website, which is briankoberlein.com. You can find me on Twitter at Brian Koberlein. You can find me on Google+. Basically everywhere. My name's unusual, so if you Bing me, then you can find me anywhere.
Bing? What is this Bing?
I have no idea.
Someone's getting paid.
No. I just find it funny when people say, let's Bing it.
It sounds kind of dirty.
It does. So does Google, but we don't care about that.
Oh, man. Oh, okay, Morgan. Now, once you're done giggling at our silliness.
The website is cosmicchatter.org, cosmic_chatter on Twitter, and you can find me at +Morgan on Google. I also have a unique name.
Yes, unique names are good. I do as well. You're not going to find too many other Galushis on the internet. I'm Noisy Astronomer, and I work over at CosmoQuest. Come please do citizen science with us. Again, we have all those images of Mercury's surface. you guys have been looking at the moon. You guys have been looking at Vesta. They look fantastic. All the classifications you've been doing. We've got science coming out of the Moon Project soon. But the Mercury Project hasn't gotten a lot of love. So go check out those messenger images at cosmoquest.org. I got very distracted when I was making the most recent tutorial video for it because there were some really cool landforms on Mercury. So go check that out at CosmoQuest. And thank you guys for watching the Weekly Space Hangout. We will be back next week. Fraser will be in charge again, but we will continue to bring the silliness and inject it whenever we can. The rest of the Hangout schedule, I think it's Virtual Star Party still happening at 6:30 p.m. Pacific. Don't know if they're starting to move it earlier yet, but around 6 or 6:30 Pacific. Sunday night's the Virtual Star Party, where you get to look through the telescopes of our astronomers around the world. Monday at noon Pacific is Astronomy Cast with Fraser Cain and Pamela Gay. They record an episode and then stick around to answer some questions. Wednesday, come back around. We have Learning Space at 4 p.m. Pacific. It'll be me and my colleague Georgia Bracey talking about science education and astronomy outreach. And we will have special guest Jess Krim, who will be showing us a classroom demonstration she does for geology involving cupcakes. I am so excited.
Yes, please.
Yes, please.
Yes, please.
Happy, thank you, more please.
I wish I could share the cupcakes through the Hangout, but you get to watch us eat cupcakes.
Get on that, Google.
Get on the cupcake delivery service, Google. All right. Thank you so much for watching, everyone. This is your Weekly Space Hangout, and I will see you later. Bye.
Hi, Fraser,
Hi.
you're not looking so well today.
I'm Fraser Cain. This is the closest I can find to a bald cap, guys. Hi, I'm not Fraser Cain. Welcome to the Weekly Space Hangout. I'm Nicole Galucci with the postdoc with CosmoQuest. Fraser is in Austin, Texas right now. I'm sure having a lovely time. So he cannot be hosting this week, so they made the very unwise decision to put me in charge. And I have with me Brian Koberlein.
Hi.
Hi, Brian.
Hi.
And Morgan Renberg.
Hi, Nicole.
So we are going to give you some of our top hits from the space astronomy news